Thank you so much for coming on. I've read some of your work, and I think it's really, really cool. It's really interesting. And I never thought about, I've been thinking about glacier dynamics and ice and things, and, you know, these different thermal and compositionally driven properties of ice, but I never thought about water. And so it is really cool to get, or to read your work and get a unique perspective on water. Yeah. So I think I just wanted to start out by just like a broad question of what makes the Arctic Ocean unique and attractive for your type of research?
So, I mean, the Arctic Ocean is really special in a lot of ways. I mean, it's the only ocean that is like enclosed and fully ice covered. I mean, we have the ice cover in the Antarctic too, but this is, you know, around a continent. But the Arctic is really, you know, like a basin that is covered with ice. So it's really nice because you can measure what goes in, what goes out, what the transformation processes are there. And, you know, then of course Greenland and the ice shield in Greenland, that's one of the, like, the areas of the world that is like terribly affected by climate change, right? So there's, you know, you had a system in balance for like 10,000s of years, and now humankind just like gave it a hit with a sledgehammer, right? And now everything gets out of balance. So in terms of research, that's fascinating because you're not describing a system in equilibrium, but you're trying to understand a system that is rapidly changing, and you only get glimpses here and there of what is changing, and then you try to, you know, make sense of it and extrapolate what will happen in the future. And, you know, I'm probably going to be alive still to find out if I'm right with all my hypotheses that I'm, you know, drawing from the little data that we're having, which is, you know, it's terrible, but it's scientifically really interesting.
Yeah, that is amazing how dynamic the environment is. For anyone not well-versed in geology or kind of geoscience in general, most of the things we study are on such long time scales that you'll probably never see them come to fruition in your lifetime. So it's amazing how dynamic, and I was wondering if you could tell me a little bit more about the different ocean currents and the geography itself of the Arctic Ocean and what makes that unique.
Yeah. So once I'm a physical oceanographer, so I have also no idea about geography at all. But, you know, the topography of the ocean, the bathymetry, how deep the ocean is, that really steers the ocean currents. So that's like, for us, it's super important boundary condition, right? And when we look at like the broad Arctic, so like the whole basin, which is, you know, from Alaska, Siberia, Norway, that has a connection to the Atlantic Ocean between Greenland and Norway. And this is where warm water from the Atlantic flows into the Arctic Ocean, right? And when I say warm, I say like 3-4 degrees centigrade. So it's not really nice for a swim, but, you know, it's really warm when it comes in contact with ice. And fun fact, like 130 years ago, there was an expedition to the Arctic that proved that the Arctic Ocean is actually ice-covered, and that has been debatable before, right? There were people that firmly believed that the Arctic Ocean has to be ice-free because of all the warm water that flows into the Arctic from the Atlantic, right? And that was a very valid scientific hypothesis, and because, you know, no one could go there, no one could check, right? And, well, it turns out the Arctic is very ice-covered. However, all this warm water that comes in from the Atlantic as something we call the Arctic boundary current that just like flows into the Arctic and then hugs the continental shelf and like flows around this basin. You know, like think of a bowl, and then you have like the water flowing along the rim because of Earth rotation effects. And this warm water, it stays at depth of like 200 meters or so, and it's isolated from the surface. And if you would bring that all up to the surface, it would melt all the ice like 4 times over or something. So, you know, that was a very valid hypothesis, that the Arctic is actually ice-free. It's not, but just because the warm water is like hidden away at depth. And one of the things I'm actually researching that's unrelated to Greenland, that's just like high Arctic research, is that the vertical transport regime in the Arctic changes with climate change. So there's less and less ice cover, and when there's no ice cover, it's easier to transfer energy from the atmosphere, like from winds and storms, into the ocean, right? You know, mixing because of waves, because of, you know, atmosphere-ocean interaction. Take the ice away, energy transfer much easier, more vertical transport, also more vertical transport of this heat that is stored away, right, to the surface. So like the retreat of ice in the Arctic Ocean could be like this vicious cycle of there's less ice, there's more mixing, there's more heat brought up, there's less ice, there's more mixing, right? So that this could be like a self-amplifying cycle.
Yeah, it seems like there's a lot of self-amplifying cycles in glaciology in general, which may not be the best area of science for there to be things like that, given our current climate situation.
Yeah. Well, it's important to understand these things,
yeah, of
right?
course,
so,
yeah.
so we have a better understanding of what will happen in the future.
Yeah. I wholeheartedly agree. So when you have warm water coming into the Arctic Ocean, from just like an intuitive standpoint and thinking about the way density works, why is this warm water sinking below cold water? And
that's an amazing question. Yeah. I heard you shouldn't say that's a great question because it makes it feel like the other questions are not great. But this was a really good one. That's totally right. Light water, like warm water, is lighter and would float above cold water. However, there's a compensating effect by salinity. Right, so saline water is heavier, and that's hidden away, like that's sinking down, and fresh water is on top. And while the Atlantic water is very warm, it's also very salty. And the Arctic Ocean receives a ton of fresh water from the continent. So like there's large rivers in Siberia and also in Canada that all go into the Arctic. So the surface of the Arctic Ocean is extremely fresh. It's cold, but it's very, very fresh. And this salinity effect on the density beats the temperature effect. So this allows the warm water, which is very saline, being at depth because it's denser than the cold but fresh water.
That's really cool to think about. What about the ice on the surface? What does that do to the salinity at the top? Because when you freeze out, then you're going to lose the salt that's in that water, right?
Exactly, yeah. So when I say fresh, it's still about like 28-30 grams per kilogram of salt. So it's still salt. You would taste the salt very much. But the deep ocean is like 35 grams per kilogram. So that's the difference. And if salty water freezes, the ice is nearly completely fresh. Not quite. It gets fresher when it gets older, but it's very fresh. And the salt is rejected from the ice during formation as a very dense brine. Like a salt, like if you pickle something in like salt, this is super salty, right? And that basically just falls through the water column downwards and sandwiches in at a depth where it has like mixed enough with the ambient water so it has reached neutral density. And that happens in the depth range of about like 30 to 70, maybe 100 meters. And this region is characterized by a very strong increase in salinity with depth. So we start at 28, 30 at the surface, and then at 150 meters we are at 35. So there's a huge increase in salt. And this layer we call the halocline. I think that comes from Greek, halo for salt or something. But it's a layer of really steep density increase. And that acts as a barrier layer in the verticals. It's like cling film because vertical transport has to work against this density stratification. So it's really hard to mix it because you have to shuffle dense water to the top over light water. And this is much easier if everything has the same density, but in the strong density stratification, it's really hard to transport something vertical. And this is exactly what shelters the surface ocean and the ice from this warm water below, right? Because there's this nearly impenetrable what's the word for you can't cross?
Impenetrable?
Yeah, I guess. It's like Gandalf with the sticks, like you shall not pass. This is like a layer of cling film in the ocean that prevents the heat from coming up. And that's basically what so far saves the sea ice. And if this layer gets eroded, and there's indications for that happening in the Eastern Arctic, around the Siberian coastal seas, well, then there's no boundary anymore stopping the warm water from coming up to the surface. This is exactly this mechanism we talked about that will kill the sea ice even faster.
Yeah.
Yeah.
And is a halocline like the one we see in the Arctic Ocean unique to the Arctic Ocean, or do we see that elsewhere?
It's not exactly unique to the Arctic Ocean, but it's, I think, one of the prominent, the most well-known haloclines. It happens basically anywhere where you have like strong freshwater input into the ocean. There's like some marginal seas in temperate regions like the Baltic Sea in Germany, where you also find a strong halocline, because North Atlantic water flows in, but you also have a lot of river discharge. So wherever you have ocean, like open ocean water meeting coastal regions with a lot of freshwater discharge, this is where these haloclines form. And some people, this also happens with temperature, so you can also have a thermocline, where you have like a strong increase in temperature. And that some people may have experienced, like personally, when you go swim in a lake in summer, and like the surface is really nice and warm. I mean, we're in Texas, probably everything is nice and warm, but in Europe where it's cold, you have like sun warming the top part of the lake and you go swim. But sometimes when you like let your feet fall down and like feel the deeper water layers, it suddenly gets super cold. And this is the same effect, just like with temperature instead of salinity, making the stratification.
Yeah. And when you mentioned that, I am curious how much of a contribution the sun has on this system, because the way I would think about it is that if you melt ice out, then you have more water that's able to, instead of ice reflecting that sunlight, now the water is going to absorb it and things get even hotter.
Yeah, that's the ice albedo effect. So if you have a white surface, it reflects sun. If you have a dark surface, it absorbs the heat. It's like wearing a white and a black T-shirt on a sunny day outside. It's one you should do, one you shouldn't. And that's also something that is one of these like self-reinforcing cycles. The more ice melts, the more heat the ocean can absorb. And this heat that is absorbed during summer, that has to be released in winter first to cool down the surface ocean to freezing temperature before ice can form. So if you heat it up during summer too much, you will delay sea ice formation in fall. And, overall the ice is then thinner, it doesn't have so much time to grow during winter. It melts earlier, so it basically prolongs the open water season with, all these effects that open water versus ice has, right? Because when we talk about sunlight, this is important for the ecosystem in the Arctic, right? When the sun shines, the algae get sunlight, they can grow. That like kind of kickstarts the whole ecosystem. And right now in the Arctic, there's a lot of endemic species, like little algae that only live in the Arctic, and they are highly specialized, right? They have all this adaptation mechanism of, timing when their larvae reach the surface to like grow for the zooplankton that feeds on the algae. And then the algae are also, I'm not a biologist, right? But they seem to be really amazing. So however, when the sea ice seasons get longer now and the conditions are warmer, more sunlight, and maybe also more nutrients because the mixing increases and drags up more nutrients from deeper layers, the Arctic might become, nicer for species that lived in the Atlantic. And then they migrate into the Arctic, and in a direct competition, they outcompete the Arctic species. The Arctic species only have the advantage because they are so highly adapted to these super hostile conditions. But if the conditions become, nicer for everyone, it's probable that like the endemic species get kicked out by the things that come from the Atlantic, because, when we talk about fish, for example, like the higher classes, an Arctic cod is about like this size. I don't know, what is this in inches? I have no idea. Maybe like
that's
2,
about like
3,
7 inches,
wow.
yeah.
Okay, this is an Arctic cod, and this is an Atlantic cod, which is
7 inches versus like 3 or 4 feet.
Yeah. So, and direct comparison, if they like hunt for the same prey, you can think about who wins, right? And by now it's still titled the highway to death. So any species that come in from the Atlantic, they are believed to, they last a bit in the Arctic, but at some point they just die because they can't handle the conditions. However, there's been Atlantic cod being caught in the Arctic, high Arctic in winter, and they seem to be doing fine, right? So like there's a lot of species creeping into the Arctic from the Atlantic, which are a threat to the local ecosystem, which is, after 5 steps, a direct consequence of, climate change, changing the physical conditions in the environment that then translates all the way through the ecosystem.
Yeah, it's very interesting to me, because I remember when I was first doing some research into some of your seminars and presentations, you would talk about vertical transport and how it's transporting more nutrients that's coming from the Atlantic up into this more hostile kind of nutrient absent, cold Arctic environment. And I was like, oh, well, maybe that's good for the environment. Like, maybe that's good for the animals. But they're so specialized, right?
Yeah.
Yeah.
Well, it's good in one regard. Not sure if it's good, but it's one of these, it's not a However, so if there's more nutrients and more primary productivity, that is more carbon dioxide that gets sucked out of the atmosphere. Because if algae grow, they utilize atmospheric CO2, or, well, it's CO2 that is in the water, but when they decrease the partial pressure of CO2 in the water, it can take up more from the atmosphere. So that's like, trees growing just in water, the algae. And when they sucked up like the CO2 and then eventually they die, part of them sink to the seafloor, and that really, sequesters, buries carbon dioxide that we put into the atmosphere. So this is like one way to remove carbon dioxide. And the more primary productivity happens, it's like if you, plant an additional forest. It's not going to solve our problem of global warming. It is something where, at least a positive side effect of the whole disaster of climate change in the Arctic.
One very small drop in a very large bucket.
Yeah, probably, yes.
So can you tell me about the difficulty of science in the Arctic? I know that expeditions can be really difficult. You guys can get stuck out there. You're on an icebreaker. Ice can, drift your ship way, way off course, and you're stuck in a certain place for a certain period of time. Can you tell me about that?
Yeah, and don't forget the polar bears. They are the actual thing that makes polar research quite annoying. So a couple of years ago, I was on a year-long expedition in the Arctic. So I wasn't there for a year, right? I was there for like 3 or 4 months, but the expedition was for a whole year. And the reason why we did that was there's very little data from the wintertime in heavy sea ice because you can't get there, right? You can ice break with an icebreaker, but if the ice is too thick and too packed, also the icebreakers get stuck, right? So most of the data from the Arctic is from summer and then from the marginal ice zone, so like, where the ice starts, but mostly like nearly open water. So this expedition actually used the drift of sea ice to go to, somewhere in front of Siberia. It was like quite off continent already. And then we picked a nice big ice floe, anchored to this ice floe, and let us freeze in during fall with the ice. And then the ice basically drifted the ship for a year through the central Arctic. And during that time, we, did measurements for a whole year in winter and summer. And that was a pretty unique thing. And yeah, getting stuck is a thing. So for the supplies, resupply and personal exchange, we had icebreakers from Russia and China, I think, mostly from Russia, that helped us get to that German icebreaker that was frozen into the ice. And these got stuck like all the time. You can't plan, right? It's if the ice gets pressed together, you just have to at some point say like, okay, we're just not going to even try because we're just like using up fuel for nothing. And you have to wait until the ice gets a bit more loose, that like is because of wind conditions and whatever. And then you can go, but you can plan a journey for a week and it can take 3 weeks. You really have no control about, you learn a lot of patience when you're on that. And yeah, the next thing is polar bears. It's polar bear country, and you don't want to disturb them, but you also don't want to be eaten. And they're huge, right? And they're dangerous. So you have all these precautionary measures in place. There's people on the bridge and on the stern of the ship watching out for polar bears. When you're out there, there's always one person designated to just be on bear watch, has a big gun, has a flare gun to, if bear comes, to try to scare him away. And if he really tries to attack you, even like shoot to kill the bear. Luckily, that has never been necessary. But I don't know, I always felt it's a strange feeling when you stand there with like this heavy gun on your shoulder, and I'm not a big gun person. I do like the shooting part, like the hitting the target part is kind of where I suck at. But you stand there with this gun and you're like, okay, I'm going to protect my colleagues and friends now. And if it's, a bit foggy and like a polar bear could just like, come out of the sleet, out of the water and be like, hello, that's a scary thing. And yeah, and they just mess up your plans, right? You have a good plan in place, what everyone has to do on this day. It's like, chuck, chuck, chuck. And then you want to go out on the ice, and then someone's like calling in. It's like, yeah, no, there's a polar bear. And you're like, okay, we're going to unpack, we're going to wait, and then we see what happens next. So yeah, they mess up all the plans. They are really cute though, like the baby ones.
Yeah, it's really amazing how when you're walking through everyday life here in Austin or somewhere else, like you're never thinking about predators or being preyed on, but that's one of the only places you can go in the world and you would actually have to worry about that. And you would have to worry about, I mean, I've seen these videos of polar bears like jumping out of the ice next to seals, and you wouldn't even have thought they were there at all. It's really amazing. And yeah, really, really, I mean, I'm sure that's pretty scary, but also, is it like almost kind of majestic when you do see one and see how big they are in person? And
yes, they are. So they do look so cuddly and cute from like a bit of a distance. And when you're on the ship, right, they can't climb up the ship's wall, so you're super safe there. We do try to make loud sounds to like scare them away a little bit so they don't get used to the ship, because this is what you really don't want, right? You don't want them be like, oh yeah, this is a cool place to hang out. It's like, no, this should be a scary place for you. They are not really scared of a lot of stuff though, because they are the apex predator. Who's going to prey on a polar bear, right? They're just huge and the top of the food chain there. They are super cute to look, especially when you have like a mom with a cub and the cub is following the mom and climbing over the little ice floes. It's really, really cute to see. And they're so curious, right? They when we have installation on the sea ice, or measure autonomous instruments that measure, or like little tents, they always go and they pet the tents and they play with this and they, we had very polite polar bears. They didn't destroy a lot of things. They were very gentle with our instruments, but they're like 3 meters tall, which is, I don't know what in feet, but
it's about 9 feet.
Yeah, they're huge.
Yeah.
Maybe even more than that. They are huge, right? And they could just like destroy a lot of things extremely easily. And for most of the time, they didn't. We were really grateful for that. But yeah, it can get scary. We didn't have critical situations, which was good. We also had like a lot of like precautionary measures, right? Like whenever someone spotted a polar bear, even in the distance, this was evacuate ice, come back. So we were very, ahead of it. But we were also lucky, right? You can never be sure. And they are designed for, stealth hunting in the Arctic. As you said, like they jump out and the seal didn't notice them. They could easily, in bad weather conditions, if they wanted to. This risk is always like associated with seagoing or ice-going oceanography and sampling there. You're in their territory.
Yeah. And then you mentioned how you had to develop a lot of patience. And I remember watching in one of your seminars that you mentioned you had to personally oversee and quality control over like 1,000 measurements while you were there. Tell me about that.
Yeah, so if you are on ships or on the ice, doesn't really matter, and you do physical oceanography, the work is really repetitive. So I mean, the instruments that we operate, they are like super high, whatever, top of the art, some are just prototypes and whatever. But once you get them going and you figure them out and they don't break, what you do is like instrument down, instrument up, instrument down, instrument up. So that's can get quite boring at some point. If you don't have an electric winch, it also gets like extremely, getting with a hand winch stuff up, you come back and you're packed, right? You're so fit. But then like the aftermath of getting all these shiny measurements is you have to quality, like you process the data and you quality control it. So there's always like the sensors have hiccups, and then there's some things. So if you measure temperature, that's relatively easy, right? It's very straightforward. But my specialty is turbulence, and that is not so straightforward to process, right? So turbulence sensors, we use shear probes, and do you know these lighters that have the click thing, like not the wheel, but the click to make the spark to ignite them? Yeah. So the click thing is a piezo element that basically transforms pressure to an electrical signal. So, and these are also built into our shear probes, and they're like the tip of my little finger. And you lower them through the water, and when the current hits them, and the current at the upper layer is a little bit stronger than the one at the lower layer, there's differential pressure on that signal, so it bends a little bit, someone on how are the things called when you jump into the water from a tower and you go jump?
A diving board?
Yeah, like a diving board, right? So it bends a little bit, and that translates into an electrical signal. And this is we're talking about centimeter scales here, right? And and they measure at 1,000 hertz. So over 1,000 measurements per second. And what you do then, you have all these little wiggly motions detected by differential pressure that hits the shear sensor. And then you basically transform this signal from time space into frequency space, right? You make a Fourier transform. All the people that don't like mathematics, I'm very sorry right now. And then you basically fit a spectra that from theoretical considerations is known to represent a certain level of turbulence, so how many wiggly energy on small scales is in the water. And you do that for you don't do that manually, right? You have routines to do that, but you have to check every now and then, do the spectra fit, are the sensors okay? And then you do that for a whole water column of 200, 300 meters, where you have the measurements in 1 meter bins. And then we came back from this Arctic expedition, with 1,600 profiles or something from 3 different probes, and then every now and then you had to change the sensors. They have new calibrations, and I think it took me a year or so until I had a final process data set where I'm just happy to work with that and share it with the world. And every now and then I still find a profile. It's oh no, this one looks sketchy. You shouldn't use that. So I'm at version 2 now, and I think version 3 will have to be done sometime. But yeah, this is observational data, right? It's messy. And it's a lot of manual work to get it right. So that's also part of science.
Yeah, I would imagine part of your day is, or a large chunk of your day is actually out in the field, physically taking the measurements, but you would also have to take a lot of time, like you said, to go through all these data analytics.
Yeah.
And
but that's
methods.
What we do after.
You do after,
yes.
Okay.
So ship time is so expensive and so valuable. What you do there is you check, is everything still working? Just so you don't measure with broken sensors. But after you checked everything is working, you just try to get as much measurements in as you possibly can. And that's, it's fun for the first couple of weeks, but it gets really exhausting. You sleep very little. You're basically working at maximum all the time for a month straight. But it's.
Do you ever run into when you're post-processing your data, when you go back home and then you find a site that's just really weird and really wacky, and you're like, man, I should have taken so many more measurements in that spot. Do you find that?
I found that when I worked with data from a cruise that I have not been on. And this was actually, so some of our instruments, they have a live display of what we measure. So they have a cable that sends the signal, and you can see on the computer real time what the sensors feel right now. And this is really cool because then you can react, right? And especially at that cruise, they didn't have a lot of time, but they went back and they sampled around that place for a little bit where the data looked super wacky. And this was one of my favorite pieces of data, because that by chance we found, I wasn't on that cruise, I just used the data afterwards. They found a process that is a huge contribution to the vertical transport in the Arctic, and that's coming from, so you have a cyclone, like an atmospheric cyclone that passes a region of the Arctic, and that basically displaces water from the Central Ocean and piles it up at the coast, right? So it's called Ekman transport, so the wind basically pushes the water to the coast. So you have a difference in sea level. The sea level at the coast is higher than further offshore because you pushed all the water to the coast. And then the cyclone leaves again, and then the water, there's no restoring force anymore, so it swashes back because of Earth rotation that excites something that we call a continental shelf wave, so a huge wave that travels around the Arctic. And long story short, so this thing caused eventually a lot of turbulence at this specific spot, and brought a lot of nutrients up to the surface. Primary productivity was enhanced in the aftermath of this event, and just because of this. This happens like 8 times per year or so. And we were lucky enough to like capture that in data, which is super sparse, right? And super great. And there was so much going on there. So that was really great. And yes, if I would have been on that cruise and if I had somehow could convince the people that we need more measurements there, that would have been something that I really would have wanted to do. However, oftentimes you don't really see what you measure before you analyze it later on in the lab, because most of the instruments don't have this online data transmission. And even if you want to adjust your plans, it's not just you on the ship, right? You are like one working group, but there's 60 scientists and at least, 30 different working groups. They all have their agenda. They all have their dedicated ship time. And if you go, it's like, hey, can you maybe not do your measurements because I want to do more of mine? You really have to be like good friends with them or have a very valid reason, because, they want to do their measurements very badly as well, right? And, getting to the Arctic and getting your project funded to do these measurements, that's a very tedious and expensive process, right? And you don't give away your ship time to someone just because they're, oh, this is so exciting, can we do more? Maybe they do.
When you talk about the cost of ship time, I'm curious what it usually is.
That highly depends. So a day on a ship, depending on what size it is, without any like salary costs for either the sailors or the scientists, just the operational cost of a ship is between 10,000 and 20,000 euros, which is roughly the same in dollars per day. And this doesn't include any salary yet, right? So, the captain to the cook, all the scientists, they won't get paid, right? And if you add these costs to it, then it's just getting insane. Well, yeah, it's around like 10 to 20,000 a day, depending on like fuel consumption. So just to operate the ship.
Yeah. Every second there is really, really precious, it seems like.
Yeah, exactly.
Yeah.
And
so I guess getting a little bit more technical, when you talk about how water is being pushed up onto those Siberian slopes, I'm curious how that changes those stratigraphic layers that you're talking about. So you have this halocline, and you have the warm water below, and then kind of fresher, like, water coming in from rivers, and then melting ice and things like that. Do those layers stay as stratigraphic layers? Do they kind of mix together?
That's, again, an amazing question. So going back to the cyclone that pushed up the water on the coast and then exciting this wave that goes around, it also displaces these layers, right? So when the warm water was at 100 meters, the wind can push it up to from 200 to 100 meters or something. So that can really be huge vertical things. And when the water swashes back, that kind of overshoots, right? You look at a wave, right, in a pot or so. It goes up on the one side, it goes down, it goes around, and so it can also depress these layers, right? So you can, and this is what we observed during this, wacky event that I was telling you about. This one once in a lifetime, once in 8 times per year, but it's super rare, right? And we saw that these layers of density, we call them isopycnals, right, because it's the same density interfaces. They were really pushed down in the water column by over 100 meters, like around 130 meters. So, if the freshwater layer ended at 50 meters, it now got pushed down to 150, a lot. This is, and this is not stable, right? This water doesn't want to be there. This water wants to be where it feels comfortable. These interfaces start to oscillate. You can think a little bit of a wave at the top of the ocean, like at the water-air interface. You have waves at density interfaces as well. They are called internal waves. And they work a little bit different than surface waves, but they are waves at a density interface. So if you imagine, a layer, like in a glass, you layer oil and water, that has a density interface, and then if you tap at the surface, you will also see there's movement at the interface, and it's not the same movement as the surface. That's an internal wave, and they happen in the ocean, and they follow mathematical rules because they're waves. They have their wave equations, and one of them is that they interact with Earth rotation effects. So waves of a certain frequency can't propagate further north than their critical frequency. because then Earth rotation effect kind of like catches them and doesn't let them propagate away. So the further north you go, the higher frequency internal waves you have, because the low frequency ones, they just can't get up there because Earth rotation catches them and they basically swirl around. If you look at the wave equations, it becomes way clearer. We won't do that. However, if this wave can't propagate away and say like, goodbye, it just breaks and dissipates its energy locally at the formation site where, had this depression of isopycnals. So you imagine you push down these water layers. They want to make a wave, but the wave can't escape Earth rotation effects because it's like too low mode, too low frequency. And then basically all the energy in this wave just like explodes at the continental slope where it has been formed. And this is what made this mixing event that we had observed. And this is maybe not as exciting for you, but it was extremely exciting to me to see that 300 meters of water column, right? This is like a deep, deep ocean, right? And any density gradients in the vertical, and there were huge density gradients there, right? They were completely eradicated. So this was completely homogeneous. It's like, think about like a soup pot that is 300 meters deep, and there were like all these layers of whatever vegetables, and someone steered that whole thing around, right? So it was like homogeneous, like well mixed, all the way top to bottom, 300 meters.
That's
this
amazing.
is, I mean, just imagine the energy that was necessary to do that, right? And like this find was just, I wrote 3 papers out of that, 2 papers, because it was just like such a wacky event.
Yeah. And how much time does it take for that to resettle after everything's been mixed up?
Good question. So what happens after you basically stirred this whole water column over? We don't really know what the horizontal imprint of that was, but I would assume something in the order of 1 to 10 kilometers. And when you have this blob of homogenized water, that is unstable compared to the surrounding waters, right? Because like in the distance, you still have the strongly stratified ocean, and then you have this blob of equal density water. And what happens then is something we call a gravitational collapse. And this layer basically flattens out at the level of neutral density compared to the surrounding waters. So it's basically, it turns from a blob, like a sphere, into like a disc, and then dissipates as a layer to the sides.
Oh, that's really cool.
Yeah, so it goes from like, and this also makes a lot of lateral transport, right? If you imagine there was like a lot of sediment suspended in this blob, and if this blob collapses and spreads out to the sides, it takes the sediments from the slope with it, and parts of that end up on the shelf on the one side, but other parts end up in the deep ocean, and they sink down there, and this is a mechanism that basically connects the shelf to the deep ocean, and also a mechanism again for carbon sequestration, because shelf sediments are high in biomass, but they're still mobile, so that can go back into like the cycling. But if it's going into the deep basin, it gets buried and taken out of the system, which is good again because we want to have this carbon removed, right? Yeah. Back to the gravitational collapse. So it's believed that that happens relatively quickly on a matter of like hours to days. So this spread out of after the turbulence decayed and there's nothing to continue homogenizing this blob, that's going to be gone within a day or 2.
So in like a geologic context, it's almost like an instantaneous event. Yeah, that's really amazing. Yeah, I'm thinking like if I were a bird looking down, you would see all of this like, normally stratified ocean layers surrounding this kind of blob that you're talking about. And this blob is getting all mixed up and kind of, it's probably not like a...
Yeah, but you can think of it as a surface anomaly, right? Because it was summer, so the surface ocean was relatively warm, and where you had this strong mixing event, you brought colder water from this intermediate halocline up to the surface. You also brought warm water from like, the deep part, the Atlantic water up. But overall, that was a negative temperature anomaly. So if you were a bird flying over that, you would see like, oh, warm ocean, relatively constant temperature, cold blob, warm again. Right, so it was probably like a circular imprint of a very cold anomaly in the ocean because it was summer.
And when you say that this blob kind of spreads out, is it spreading out under the halocline, or is it spreading out under that freshwater layer, or?
That depends. So this blob has a certain density, and it will spread out exactly at the vertical level where the surrounding waters has the same density. So In our case, that would have been like at the lower parts of this halocline.
Got it. Okay.
At a depth of like maybe like 70 to 100 meters.
Mm-hmm. So it depends on like what you're kind of mixing into that blob, and then so how long you've been mixing things. And,
exactly. Yeah. So the density in this blob is basically, if you mix the surface waters and the halocline waters and the Atlantic waters, whatever you have in that water column together, and then you take the mean, right? And then that's your end density. And this is also where it sandwiches in.
Mm. And then I'm curious about, is there any relationship between the magnitude of the slope, so how steep your slope is, and then maybe it has some relationship with the turbidity or something like that?
So if we go a little bit away from the Arctic, because this is a tricky environment, and to more temperate latitudes, there is something that we call a critical slope angle for internal wave breaking. So when we go back to internal waves, right, these waves at a density interface, one of the most common frequencies is the frequency of the diurnal tide, because diurnal tides, when they hit like topography like a seamount or a ridge or whatever, they get converted, like the energy gets converted from the barotropic tidal energy, so just like pushing water left to right, to a baroclinic internal wave tidal energy that is more sheared, so that goes up and down. So just like imagine a seamount and then a tide going from left to right, and anytime it hits the seamount, it kind of topples over and it, depresses or lifts up the density layers, and then it makes these waves at the wake of the seamount, right? And the frequency of the forcing, which is the tide, determines the frequency of the internal wave. So there's a lot of internal waves at tidal frequencies. And now to the slopes. Depending on the stratification of the water, so like the density layering and the angle of the slope, there is an angle where internal waves do not reflect. So they reflect in a weird way. They always reflect relative to the horizontal, whatever your slope is, right? When you have light in a mirror, like incoming angle is equaling outgoing angle. Same for internal waves, but it's not the slope that is the reference, it's the horizontal. So if the slope has a critical angle, the waves don't impinge and get reflected. The waves come and they would be reflected in parallel to the slope.
It's exactly like light. If you have like a critical angle with light, then, or if you hit like a laser on a prism at the correct angle, then it just refracts like exactly parallel with that, and then you wouldn't see a reflection at all.
Oh, right. Yeah, so then I have no idea about light, but good thing. But if that happens, this doesn't really work, that it goes in parallel to the slope, because there's like a lot of physics preventing that. So what happens basically there, it dissipates into mixing. So it makes this boom in the water column where it just like makes a huge ton of mixing, and it lifts up all the sediments from the seafloor. And this happens extremely frequently, not in the Arctic, but at lower latitudes, where these internal waves of semi-diurnal frequency can still propagate freely, because they can't in the Arctic, right? Because of these rotation effects at higher latitudes, they just can't. They don't move around anymore. But where they can, they every now and then hit like these critical angles at continental slopes, and this is where you often have very turbid layers in the water, and they're called intermediate nepheloid layers, which basically is like intermediate dirty layers. Whether the sediments from the slope get lifted up, and then basically, because of what we talked about, like, these layers, the mixing creates a layer of homogeneous density, like this blob, and the gravitational collapse of this blob basically shoots these sediments out to the open ocean at this interface, because it's basically, it's a signature of this mixed water that is unstable here and gets collapsed and spread out. And so you have the slope, and then you have like these tongues of muddy water sticking out, which is a very common phenomenon along continental slopes of the world.
Yeah, I think I saw some of that, and that's a good explanation. I was looking in one of your papers, and I saw like those tongues that you're talking about, and how they have like a greater concentration of different sediments, and they also have like I think this was a computer model, so it wasn't observational. But
that was observational, actually.
Oh, really?
Yeah, that
okay.
was from the Arctic, and this is exactly the process I explained. It was just not a freely propagating internal wave. It was this weird internal waves that can't propagate away. When we talked about this wacky process earlier, with the cyclones that make like the water to the coast, and then the continental shelf wave, the depression of the isopycnals, and then the wave can't get away but dissipates into mixing. This is what we were describing there. And that also got like the sediments up, and the gravitational collapse process afterwards, that's the same as at like lower latitudes. Fun thing was, this was the first observation of such a layer so far north. Because the typical creation process, like the freely propagating internal waves of tidal frequencies, that doesn't work in the Arctic. But there's other mechanisms that work, which is always exciting when you find a new mechanism, right? This is for people that are so process study oriented like me. That's holy grail.
How exactly did you measure that?
Turbulence we measure with these shear probes that I talked earlier, these little piezo elements that wobble around. And turbidity, we have optical backscatter sensors. So they like little sensors that emit light, and they see how much is reflected. That's for optical backscatter. We can also measure chlorophyll A fluorescence as a proxy for biomass. So like the algae, they do photosynthesis, so they have like this chlorophyll A. I'm not a biologist, but the green stuff, that's what they need for photosynthesis. And we can also measure that with optical backscatter. So light emitted on a specific frequency gets reflected from the green parts. So we have an idea of how much like algae biomass is in the ocean. And then we also have sensors that can measure nutrients, actually, nitrate at least. So you can measure all the nutrients in the lab if you take like actual water samples, but there is one sensor that uses ultraviolet lights to get an idea of how much nitrate is dissolved in the ocean. And this is where I start believing in witchcraft, because I have no idea how that's possible, but apparently the engineers found a way to, measure nitrate concentration in the water with an optical sensor, which is great, right? Yeah, and then we have, of course, temperature sensors. We measure salinity via conductivity, so it's a little conductivity probe, and then from that we can calculate how much, like the salinity content of the water. And and then the last instrument that I'm using is an acoustic Doppler current profiler. This is another witchcraft technology. So that thing, you can put it like in the ice looking down, or at the seafloor looking up, or wherever you want. And that thing sends out an acoustic signal that gets reflected on little particles in the water that are supposed to drift freely with the currents. And when this acoustic signal gets reflected via the travel distance, it knows from which layer it gets reflected, so which distance. And from the Doppler shift in the frequency of the acoustic signal. When you have an ambulance that passes, it sounds differently when it comes towards you than when it goes. It's the Doppler effect that I don't really understand, doesn't really matter, but with this Doppler effect, they can also estimate how fast this particle that reflected the acoustic signal is going. And with this one single instrument, you can get a profile of how different parts of the water column move, which is, I think that's total witchcraft.
Yeah, that's witchcraft is a good word. Yeah, that's amazing. The fact that you're able to use the Doppler effect in that way is crazy to me. I pretty recently, I was out on like a field camp, and we were using to like sparker seismic in the water, and this thing called chirp, and basically it creates like a seismic wave in the water. It's like snapping your fingers in the water kind of, but on a much grander scale. And then you have little sensors that you tug along the boat, and they can pick up the acoustic wave as it travels down to the seafloor and then comes back up, and it'll travel through the seafloor to the different layers, and then like different waves at different frequencies will come up, and you can get a seismic image. But the fact that they were able to do that with the water column is absolutely unreal. That's amazing.
Yeah, isn't it? Engineers are doing a great job in that. And like this instrument that I was talking about, that was invented, I don't think, it was quite recently, like in the 1980s or 90s or so when it became popular. Before that, current velocities were measured with like little propellers, and there was a counter of how many rounds the propeller did over time, and then you could calculate how fast the water was flowing at this specific point in the water column, right? But when they like got big in the 90s or something, that really revolutionized how we do physical oceanography, because suddenly we could get long time series of highly resolved velocities, which is a total game changer.
Mm-hmm. And does that measure the entire water, like, so this like 300, 400, 500 meter water column, it'll measure the entire thing?
So they come in different tastes. So they are like low frequency and high frequency ones. And you always have to, if you want to have it high resolved, you can't look very far. So there are ones that can really give you every 10 centimeters a reading, but they only go for like 2-3 meters in the water column. But there are ones that have bin sizes of like 8 meters, and they profile all the way down to 1,000 meters. Also depends a little bit on how much particles are in the water. So the Arctic often has the problem that there's just not enough stuff in the water to reflect the acoustic signal. So some of the like high frequency instruments, they just don't get enough signal back to make readings. So that's sometimes an issue. But if you have enough backscatterers in the water, you basically can look down for kilometers, which is it's really amazing.
That's so amazing. How big are these instruments?
Depends again on how far they cook. So the high frequency ones are relatively small. So the ones that give you like 10 centimeter resolution but only a couple of meters range, they're basically like like a something that is this size, and you can carry that easily like a like a brisket.
Yeah.
We're in Texas.
Like
brisket
a brisket.
size.
Okay.
It's circular though, like a cylinder, but it's maybe like a human head size. And then the ones that are low frequency, that really are the far-sighted ones, they're huge. They are like around 7,500 kilograms, so heavier than a person. And when you have all the gear to like mount them and hold them in place, they can easily weigh like 2 average persons. And they are about maybe as tall as I am, and the transducers are the size of a big pizza. So they are huge. And like they are typically, so we installed one of them through the ice looking down, that was a major undertaking, because you don't have like cranes or stuff. That's all, like you have a lot of people and a lot of like wood beams to like try to like angle stuff up and down. And they are sometimes also built into like the ship's hull. So like you have one at the bottom of the ship looking down. So that's the big ones.
That's really cool. And I want to revisit the frequency of the internal waves that you're talking about. So when you say that they're at the same frequency as the tides, are you saying that it's kind of like a multi-hour, like goes with the high tide and low tide, or is it with like the different tides? So there's like neap tide and then the different classification tides.
Full disclaimer here, I'm not an expert on internal waves, nor do I want to be an expert on internal waves, because they're super complicated. But yeah, you're right. So if I say tidal frequency, that's like a 12.5 hour for like one up and down cycle. And this would also be what the internal wave would have. So when you look at the current velocities, this is like a very sheared signal that you are seeing, because it goes up and downs and makes all wacky stuff to the currents. But yeah, so whatever excites the internal waves sets the frequency of the internal wave, right? So if it's a tide, it's going to be on tidal frequency. But a lot of internal waves actually come from like wind input. So you have wind events that, as we talked about, like they kind of like displace the surface of the ocean a little bit, then the surface of the ocean wobbles back. That also makes an internal wave. And that is mostly determined by so there are ones that are determined by topography. So if a basin has like a resonance frequency at which it likes to swing, that's like topographic waves. These are happening. And then there's also internal waves. They peak at the critical frequency associated with the latitude, because I told you like they can propagate freely up to a certain latitude depending on frequency. And so they can't cross this latitude, so they kind of gather at that latitude band. So and when we talk about like, as in the Arctic, so when you're at like 47 degrees north, that is the critical 74 degrees north, that's a critical frequency for semi-diurnal internal waves. And then at temperate latitudes, in Northern Europe, it's 17 hours. Closer to the equator, it's even longer periods. So that kind of like sorts out where the internal waves peak, or the frequency at which internal waves peak is set by the latitude, because it's like a barrier they can't cross, so they just like hang out there.
Okay. And then when you think about the way the ocean is circulating in the Arctic, is there, so there's water coming up from the Atlantic through that eastern side of Greenland to the west of Europe through the Gulf Stream?
Western side of Greenland. Between Greenland and Norway. No, that's east. You're totally right.
Yeah.
I'm terrible with
No,
directions. Yeah.
Of the eastern side of
yeah,
Greenland.
it's more like on the western side of Norway, though. So
yeah.
It's like a two. So because of Earth rotation effects, currents always tend to, on the northern hemisphere, want to have like a topographic boundary to their right. So the Atlantic water comes in and
I'm just now getting that.
Thanks. And the Atlantic water hugs the slope in front of the coast of Norway and then Siberia and then goes around. And you have an outflow that balances that on the Greenlandic side that goes south. And that basically there's recirculated Atlantic water at depth that goes out. And at the surface there's like all the fresh water that comes from Siberia that goes like along, once crossed the Arctic and then also gets exported as the East Greenland current, I think it's called, but it's going parallel south on the eastern side of Greenland. So and this is like this exchange flow in this connecting strait between the Atlantic and the Arctic. It's called the Fram Strait, by the way. And you have like a similar effect between the Pacific and the Atlantic in the Bering Strait. But the Bering Strait is like, I don't know, thin ice here, I think just like 50 meters or 75 meters or so. It's super shallow, while the Fram Strait is like 2,000-ish meters deep. So like this is, the one is like a little back door and the other one is like a huge gate that is open, right? So most of the exchange happens on the Atlantic side. People that do the other side of the Arctic would disagree here very much, because that's also very important. There's a difference in what mass can be transported.
And is there a point where that warm water that's coming up through the Atlantic plunges down underneath the halocline? Or is it always kind of located at depth?
So yeah, that's a good point. So when it comes in, it's relatively close to the surface. And then because of the exchange with the atmosphere, it loses a lot of heat to the atmosphere. And so people say it dives down, but that's only half correct as an image, I think, because what it actually does is, while it propagates, the upper part of this water layer gets eroded by mixing, right? So it's like, I know I can't come up with like a good, visualization of that, but it propagates, and at the surface there's always something going on. Like there's mixing, this heat loss upwards, and the more heat it loses, and the more of its properties it loses, that kind of becomes the halocline, because there's the brine rejection from sea ice formation. There's just a lot of going on at the surface, and so like the upper part of this Atlantic water that gets entrained into the upper part and loses its properties, and it's just like scrapped off more and more and more. So you see that the Atlantic water layer starts deeper down, and it looks like there's a slope that plunges down, but what actually it does, it propagates very steadily, but the top part is eroded and grated off more and more and more. So it just looks like it dives down, but actually it's just like lost to the surface by like overlying mixing processes.
Yeah. So like, instead of thinking about a tunnel of water that's just like a roller coaster shooting down, it's more like you're kind of like
a carrot that gets grated off, or like a piece of cake, like you grate off the surface. Yeah.
Okay. And I'm curious how these vertical mixing processes that you're talking about affect the sea ice itself.
Yeah, so the one thing is that if you like mix heat from deeper layers up to the surface, they become available to melt sea ice or to warm the surface and delay sea ice formation, because you need to cool water that is warm for a longer time, so it becomes cold enough that ice can form. So that's bad for the sea ice. Then the turbulence itself also exchanges the water that is in direct contact with the sea ice. So, for example, in spring when we have melt season and the ice is melting, and the very fresh water typically stays close to the ice if there's no mixing away, right? And then forms like, a layer around the ice. But if you have a lot of turbulence, you basically scrape off this layer and exchange the water at the ice-ocean interface more frequently, and this also brings like a little bit of heat to the interface every now and then, so the ice melts faster. It's like, think of a drink with ice cubes. If you let it rest, the ice doesn't melt as fast as when you stir it all the time. So this is the effect of turbulence on ice melting. It's, if you stir a lot, you basically exchange the water that the ice interface experiences very frequently, and that's always like a little bit of heat, and that just increases melting.
So you're advecting heat instead of diffusing it just through the water itself?
Well, turbulence is a fun thing when we talk advection diffusion, because, the only diffusion that actually happens in the ocean is molecular diffusion, right? And this is super slow. However, what turbulence does, these little whirly motions, it enhances the interface between, for example, cold and warm water. So molecular diffusion can act more efficiently, right? Because if you have whatever interface and then you triple, double, quadruple the interface, molecular diffusion just acts so much faster. And it's technically, that's an advective process, right? Creating these big interfaces. However, this is happening on so small scales that we really can't even start to resolve that. So we basically lump it all together in something that we call like a turbulent diffusivity, which basically says, oh, how strong is my turbulence that creates on very super small scale advective processes these interfaces on which molecular diffusion then can actually act. And this is what sets it, right? So how much turbulence you have, that tells you how fast your water diffuses, and you don't even have to worry about molecular diffusion anymore, because it's the underlying process, but the thing that really sets how much on a meter or tenths of meter scale two water masses mix is how much you stir it and how much you enhance interfaces that allow for diffusion. So advective is right in that regard. We would still call it diffusive because it's turbulence that makes these wiggly motions, that enhances the interfaces, that allows diffusion to act more efficiently. But you're technically right, it's advection. We just would call it diffusion because it's, the interface enhancement thing with the turbulence. Does that make any sense?
That makes sense. It's not so much. I'm thinking of it from a glaciology perspective. So when I think of advection, I think of this warm pocket of ice that's transporting itself downstream, and the diffusion along kind of the boundary of that warm ice versus the cold ice is happening so slowly compared to the advection that you can just think of it as this hot blob that's moving through space. But you're right, it's not the same with water because
water moves,
it's a liquid,
right.
It's not a solid,
yeah.
Right? So
and that can also happen in very low turbulent environments in water. Then you can really have cold blobs of temperature anomalies that gets transported with the water. But even if there's low turbulence, there's always some movement with water, right? So at some point, and probably much faster than in ice, this blob will dissipate because of diffusion. And what really sets how fast it will diffuse is more the turbulence rather than just the molecular diffusion.
So generally speaking, just to kind of summarize, these big, huge mixing events have a negative effect on the amount of ice. So you're going to melt some ice every time you do have one of these huge mixing events.
Maybe. This is tricky, right? So, this is the one effect that it does. It brings heat up. So in summer, in our case, it actually reduced the surface temperature because, there was sun shining, the surface was warmed, and halocline water entered the surface layer. So that would probably have been good for sea ice. However, we were talking about time scales, right? And like this anomaly will just, gravitationally collapse, spread out at an intermediate level over the course of like a day or so. So that really doesn't play a role for sea ice formation, this individual event. However, what does play a role is it brought some heat from the Atlantic water layer up to a layer that was further up in the water column. So it's closer to the sea ice now. If it can reach the sea ice or not, and on what timescales, that's kind of unknown. We don't really know. But overall, more turbulence brings up more heat from the Atlantic water and is not good for the sea ice in general. In summer, turbulence could also bring down heat from like sunshine on the ocean to deeper layers, which could be good for the ice, like, delay ice from melting when it's in spring. But we don't have like a lot of good data on that. And turbulence is one thing that you can simulate extremely poorly because, it happens on so small time scales. And when we look at our ocean models for the Arctic, they have a resolution of 10 kilometers in the horizontal and then like a meter in the vertical. So, and you will like imagine how small like these little turbulent wacky motions are. Yeah. And this is you have to like eyeball it kind of. We call that parametrizations, and they are all terribly wrong. They do an overall surprisingly good job, but studies on turbulent effects on whatever are super tricky because the data is sparse and the models are incorrect. So this is really a part where we have a lot to learn still as a science community.
Mm-hmm. So what are some of the ideas for future work that you guys want to do? Maybe better models, more data?
Yes, that's basically. So, we have a lot of data that still needs to be analyzed, right? So the data from this campaign I was talking about, the 1 year in the Arctic, the 1,600 profiles, I've done a little bit of work with that. And I've just submitted a proposal to NSF to get funding to do more work on that because that was a pain in the butt to get all this data and was so expensive and so much work, and now it's there. And what I feel the next logical step would be, this is a very unique data set, so no one has ever sampled under ice turbulence to that extent and in these many different, like for a whole year, right, all the seasons, and then we drifted across the whole Arctic, so there was a lot of like ambient conditions that all influenced the turbulence. And what I really want to do, what I think is a crucial next step, is take this data set and try to set up a model that basically, just one dimension of the water column that goes with these measurements and test how different turbulence parametrizations, the things where we eyeball the effect of turbulence, there's like a whole suite of things that try to approximate that, and none of them has ever been tested for under ice conditions. So I want to take my under ice turbulence measurements and test all these different turbulence parametrizations, see how they perform, what are their limitations, constrain the parameters that are involved to basically see how good can we get with simulating under ice turbulence. And then you could take these parametrizations and plug them into like the big models that actually do the simulations of the whole Arctic. And I think that would be a huge contribution to reduce uncertainties in ocean models, but they are part of also climate models, right? And like I feel like this is one of the big things that need to be done and that also can be done with this exact data set that is very unique. So I hope NSF also thinks that way, and I get funding to do that.
Yeah, it sounds like an amazing proposal. Best of luck with that.
Thank you.
I know those are a lot of work, and it can be a pretty tedious process, just getting proposals in general. I remember you mentioned Doug earlier. I talked to Doug because when he came on here, he had just submitted a proposal too, and there's like
this is our job, right? Submitting
so much headache with like getting it to administration. Then you got to wait a couple months for it to kind of go through all the eyes that need to look at it, and it just seems like a headache process.
Well, yeah, it's when you do NSF proposals, they have the PAPPG, the proposal whatever guidelines for how to submit a proposal, like what are the structures, what are the different kinds, what are the documentation that you need, what is the page limit, what is the font size. This document has over 200 pages. And before I submitted my first NSF proposal here, I read them all. And halfway through, I was texting our administrative lady that helped me submitting. I was like, "This is a terrible book. I don't like it." And she was like, "Yeah, and also there's a big chance that it doesn't have a happy ending, and you only get to know that after like 6 months, because you put all this work into like getting this proposal ready, and like there's the science part, but then there's also the formalities and administrative part, and then you submit it, and it can happen that after 6-7 months you hear back, and they're like, not today, honey." And that's science, right?
I'm curious, I guess personally, about how much funding in general is kind of going into Arctic science, because I know that now that there's more ice retreating, there's a lot more of a government presence of the U.S. and Russia in that area, and I know that they're trying to get science going. Has that created more opportunities in your field, or?
I think so, yeah. So there's, science is always political, right? And if the government is interested on, for example, having more presence in Greenland, they are also interested in doing scientific research in Greenland. So NSF actually made it possible, which I think is really nice, that you can actually fund scientists in Greenland, like Greenlandic persons living in Greenland, not US people, with US government money in joint projects with the Americans, which is amazing because there's a lot of science going on in Greenland, but there's a lot of scientists just, going there, doing their science, leaving, and, the local people are completely overwhelmed, also the local scientists and the government. It's just like, there's so much happening in our country that we have no control over, we don't know of, and we are also not involved in, which is kind of, just imagine some foreigners coming to the States and it's like, yeah, I'm gonna like probe your soil. You're like, no, this is not good. But this is exactly what happens in Greenland, right? So they're like, I feel like they're emancipating themselves a little bit. So they formed now the Greenland Research Council to like starting to set up like, rules that you have to get like permissions for certain things, and so it's a good call of NSF that, in my opinion, that they now allow that you want to have projects in Greenland involving the local scientists, as you should do, that you also provide means to fund them so they don't have to do it for free, right? Because there's like, I don't know, there's more than 5, but like a very, very small number of natural scientists in Greenland and a huge number of natural scientists in the States wanting to work in Greenland. So they're just like overwhelmed with the amount of like, hey, you want to collaborate on this proposal with me, things that they get. So yeah, it's good that you can actually give them some money for their work, it's really good. But yeah, I don't know exact numbers, but I know that, for example, NSF has a call that is called, I think, Arctic Research Opportunities or Arctic Natural Sciences or whatever, and they distribute like, I think, 50 million annually for science projects, and this is just like one way to get funding, right? There's also like a lot of funding coming from NASA and NOAA and ONR, and I think there's quite some money being invested into Arctic research, and climate change and Arctic being disproportionately affected by climate change. It's actually beneficial for my chances for funding, right? Because this is just, I happen to be in the lucky position that I do research at a very politically relevant topic, which kind of makes it easier to fund that compared to other things.
And when you're submitting a proposal to different organizations, so let's say NSF or NASA or NOAA, like you mentioned, is there like a certain shared narrative of the organization or like a shared objective that they want to accomplish, so you kind of have to cater to that?
Yes, so I'm most familiar with like how funding works with NSF, and they have solicitations for the calls. So they basically it's like, hey, so we have this Arctic natural sciences, and we want to fund projects that work interdisciplinary, that address societal needs, that do this, do that. So they basically, they compile a scope of projects that they want to fund, and then you have the science that you really want to do, and you basically see how it fits into that scope, and also adjust your direction of research a bit. And the nice thing about, so I mean, one could argue now that's like you try to like, you know, squeeze your research into what is wanted from the politicians. However, NSF, that's also scientists working at NSF, right? And there's feedback from the science community to NSF. There's political stuff from the one side, but they also try to make sense of what is the research society or the US society needs right now. What is the things that we really want to explore? Do we want to do Arctic or do we want to do tropical ocean? Do we want to have large-scale phenomena or do we want to do like fancy little, that's like, do you want to spend money to go on the moon or do you want money to go to the seafloor, right? This is a political decision. However, the science it triggers is guided into this political direction, but also making advances in that field. And it's because it's this dialogue with scientists, it's actually also a good thing that me as a scientist who would just be happy to do science for the science sakes is forced to think about what are the impacts of my science, right? Which questions can I answer that really matter? And so in that sense, it's actually an okay system or good system. I don't know. All systems are kind of weird and not perfect, but this is, you know, a way how scientists are guided to actually think about what of their science and their work actually means something and makes sense for society to know about things.
Yeah, it seems generally healthy. Everything has its pros and cons, of course.
Yes.
Yeah.
Yes.
Can we talk about Greenland a little bit?
Yeah, sure.
So when you mention these kind of wave processes and the different processes that are going on in the Arctic, how is Greenland different and how is it similar to that?
Yeah, so I mean, we were talking mostly, nearly exclusively about like, you know, the high Arctic, the offshore ocean. Greenland is different because the oceanography I'm doing there is in the fjords, you know, and the fjords are like super narrow, super deep, super long incisions into the mainland. And most of them have like a little sill in front, which kind of shelters them a bit from the surrounding ocean. Right?
So there's like a pile of sediments that kind of come up. Is that what you mean?
So this is something to ask Benji maybe,
Yeah.
because he's like a sediment on paleo time scales. My understanding is that there was like, you know, glacier flowing in and that like pushed all the dirt and everything, and then it made like this pile, but it's not dirt, it's like super solid rock by now. I don't know how that happens, but this is paleo time scales that I'm absolutely not familiar with. I just take, you know, seafloor as a given for me. So I'm not thinking about that. But the thing about these piles of, or like these sills, like these very shallow parts of the fjord close to the shore, close to the ocean do, is they shelter the deep water in the fjords. Fjords are like hundreds of meters deep, and the sill is maybe like 200 meters deep. Differs from fjord to fjord, but this is the dimensions. And that kind of constricts the exchange with the open ocean, right? Because if you have like this obstacle, you can't just exchange water. And that is important because we again have like influence from water from the Atlantic, because it's still like close to Greenland, right? It's the subpolar North Atlantic that is around Greenland. And that's relatively warm at depth still, and that every now and then flows over the sill. And once the heat is in the fjord, it eventually propagates further inland and in parts might reach the glacier front. And, you know, warm water and ice melting. Huh? And so this is one of the things we're very interested in the fjords, is how is the exchange between these narrow and kind of sheltered fjord systems with the open ocean? How is the progression of warm water that flows in from the open ocean within the fjord? And then how much does the fjord water melt the glacier fronts that terminate in the water? And there's so little data, and it's such a complicated system that there's really, because a fjord, it's also not just one, this is branches of fjords, and there's so much going on there. And yeah, it's really, really tough to do. And we have one project in Greenland right now that just got funded from NSF. Thank you very much, NSF. That is about, we want to set up a computer model of one of these fjord systems to better understand how is the exchange, how is the transport, and so on, and how is the melting of the glacier fronts. And then we also want to see how the physical oceanography, so the transport of water and also the mixing, me mixing person, always for the mixing, affects the distribution of nutrients, for example, like, the transport of nutrients from deeper layers to the surface, which affects the primary productivity, algae growth, which then kickstarts the food web, and like the zooplankton come and the fish come. And we want to find out where primary produced material ends up at the ocean floor, if it gets transported to the side and then sinks down, or if it sinks down here, to try to see if the distribution of benthic habitats, benthic means living at the seafloor, so of seafloor habitats can be explained with physical oceanography conditions, which is a long shot, but you have to start somewhere. And the nice thing about benthic habitats, so that's like corals are living here, sponges are living there, and they have different preferences, right? Corals, they want to have relatively high ocean currents because they don't like too much mud accumulating on them. They also need fresh food, so they want to be close to a spot where there's a lot of algae growing, which is probably a spot where there's a lot of turbulence happening that brings up nutrients. And then there's sponges, which are I eat whatever's left, right? 3 weeks dead, give it to me. And then there's places where nothing at all grows, and then there's places where halibut fish accumulate. And the nice thing about corals and sponges, in contrast to fish, is they don't move. So physical conditions, they are kind of always the same. So there's mixing hotspots, there's transport patterns. They vary, but the big picture is kind of always the same. And also for benthic habitats, they're kind of their distribution doesn't change on short time scales. Fish, however, if you want to see where's a hotspot for fish, can be there's a hotspot today, but not tomorrow, because the fish decided to migrate. Fish are terrible to understand. Sessile organisms, much better. So this is what we're trying to do, get the physics and the biology together, which is a long shot, but we're going to try. And we have we have a great campaign lined up. So we go there, I go there in September, and hopefully already do some measurements of turbulence and potential turbulence hotspots. And we're going to have a winter campaign where we go on the frozen fjord with ski-doos, and we ski-doo all the way to the glacier front, as close as we dare to go. And you can't go there in summer with a boat because there's still too many rests of sea ice and little icebergs, and so too dangerous. But in winter, everything is frozen, everything is a bit more stable, and then we just ski-doo. And then drill a hole in the ice and measure from the ice, which will be a super cool adventure.
That is really cool.
Yes.
Are you trying to measure properties of the ice and kind of constrain what the ice is putting into the fjord, or?
Well, more of the ocean. So for ice, it's probably also great. So we're going to measure turbulence, of course, and then the stratification of the water close to the glacier. How's the temperature profile? How's the salinity profile? Nutrients. And also we're going to do camera drops to see what lives at the seafloor, so close to the glacier. Which is pretty cool. And we're going to take water samples for the lab. A colleague of mine is going to analyze them to see if he can detect meltwater at different distances from the glacier, to see how much melting is actually going on in winter. Because, there's not much melting from the top happening in winter, because it's cold. But the ocean, it's still warm. So our hypothesis is that there is actually a substantial fraction of submarine melting happening in winter, which is kind of disregarded in a lot of studies because it assumes that submarine melting mostly happens when you have surface melting, and then the surface melt enters the fjord at depth, at the foot of the glacier, and then has this buoyant upwelling plumes, right, ejection of fresh water at depth that then, bubbles to the surface, and that makes a lot of turbulence, and that makes a lot of melting exactly where this water bubbles up, right? But, if you don't have that and you have warm water next to a solid ice interface, there's going to be some melting happening, right? And question is that significant? Does that matter, or does it not matter? And my hypothesis, it does matter, but we'll find out.
That's really interesting. I never thought about water, the actual meltwater from the glacier itself, from surface melting, is driving melting underneath the glacier. Is that Like when you say
not so much underneath, but it's what happens is like the ice sheet melts on top, and then the water kind of falls down, and at the between the ice and the rock bottom, it basically makes its way in little channels to the ocean. And like either it just comes out at land, at like, a glacier that is land terminating, or when the ocean is terminating in the fjord, then it comes out at the sea floor, right? And that is several 100-meter depth. And because it's fresh water, it's super light, and it just like, bubbles up. And it drags a lot of like deep water with it. So this is why fjords that have marine terminating glaciers are generally more productive than fjords that don't have marine terminating glaciers, because that's a very powerful mechanism to drag nutrients up to the surface. And you do that at the glacier front, but then it spreads out along the fjord. So the little algae are very happy because they get like an extra nutrient kick from this upwelling at the glacier front. But and these things, like physical oceanography studies these upwelling plumes a lot. So there's a big focus, bunch of literature on these upwelling plumes. And what I did a couple of years ago, I was basically looking at more the melting that happens when you don't have these massive plumes that basically override all the signals, because they only exist for like 2 months in summer, when like the surface ice sheet is melting. But in winter, they are just not there. But you still have relatively warm fjord water touching the glacier front. And also these upwelling plumes are like a couple of 100 meters wide, and the glacier front is kilometers wide. So there's the 90% of the glacier front are actually unaffected by this upwelling plume. Still there's warm water in contact with ice, right? So it still must do some melting. And also this melting produces fresh water that rises, right? So there would also be I think, and this is, don't take that as a given in science. This is like my wild hypothesis, is that even the melting that happens just for being in contact with relatively warm water is a freshwater injection that probably doesn't rise to the surface, but it's gonna like rise a little bit, and it's make a bit of vertical motion. But it's gonna do that consistently throughout the year over the whole glacier front. So there must be some vertical transport process in that. And now, how much effect does that have in the long run, in the annual mean for the whole fjord, compared to what happens in this plume that is rising up over this short distance and only for 2 months? So this is one of the questions I'm trying to answer at some point in the future. Is like, what is the, how important is this one? How important is that process?
And when you kind of try to integrate climate change into that and think about there being more melting over time, is this phenomenon going to kind of intensify, do you think?
So for a short period, so if you, first, yes. So if you melt more, you're going to have this effect amplified. But then at some point you melted so much that the glaciers retreated so much that they are either on land or in very, very shallow water, where it really doesn't matter if you do some vertical transport over the first like 30 meters. It's like, you do that, leave that, whatever. It doesn't really have an effect. You need the super deep water got up. And, once they leave the regime where they can do that, when they're land terminating or super shallow water glaciers, well, then this process will stop completely, right? And then, it's done. And this will have a massive effect. This will really be a regime shift from super productive fjords to like super low productive fjords. And this is going to be potentially terrible also for like the local economy, because, fish rely on productive ecosystems fjord, and these marine terminating glaciers are associated with good fishing grounds. And when they're gone, the fish are going to be gone. And any economy that relies on fish, or also cultural identities, right? Greenland, the local people there, their garden is the sea, they say, because there's nothing growing there. Like all the food they get, it's from the sea. And if that's gone, they probably survive because they now have supermarkets, but it's a big part of their cultural identity that's also going to be in jeopardy, because if you remove their primary food source, their traditional food sources, what's left of culture when you take away the food?
Yeah.
And the hunting and everything. So that's yeah, terrible prospect.
Well, hopefully that does not happen. The relationship that people in Greenland have with fishing goes back a long time, and it's really cool. I remember watching a seminar relatively recently of a scientist who is looking at lakes, and lakes built up from kind of summer melting, and then they kind of drain out, and they were curious about the historic record of what was happening. So basically in these lakes, and if you're listening, I'm sorry if I get this wrong. It's been a while since I watched the seminar. But basically you build up these lakes, and they're kind of welled off by an ice dam, basically. And they build up all these nutrients. They build up all this stuff that's really conducive for organic life. And then it all drains out into the fjord at once. And so you have these huge turbulent mixing events where you inject all these nutrients into the fjord, and it creates this abundance of primary productivity. And so she went back into the historic records and looked at fishermen accounts of slime on the surface from decades or hundreds of years ago. And I thought that was really, really interesting how you could intersect those two sciences.
Yeah, and I think there's a lot one can learn from indigenous communities and people who just know the area, but they know it in a different way than we do. And when you talk about these lakes, what happens sometimes, at the top of the ice sheet, a lake forms, and at some point it just drains, like a crevasse is forming, and it just whoosh, flushes into the fjord. And one thing my colleague in Greenland told me that a couple of years ago, they had one of these events of a lake draining into the ocean, and it killed all the fish close to the glacier front because there was so much fresh water that just pulled them to the surface and put them in a completely different regime. Saltwater fish don't like fresh water too much, so they all died. After that you have the recovery and everything, but there was a big dead fish event that they thought was associated with the drainage of this lake, which is this is so cool. And no one knows about that. He does, and I do because by chance he told me, right? But there's so many things that I would have never thought about, that side effect of a lake draining, that, all the freshwater input and the displacement, a fish being dragged up by freshwater from deep where it was comfortable to the surface. This is just of course that kills them. But yeah, I would have never thought about that. And the communication is so hard though, right? Because we come from the academic science thing of hypothesis and natural laws, and this is our way of understanding the world. And then you go to these communities, and I don't have a lot of experience with that, but there's one little episode, may I tell? Yeah. So we were on a Greenlandic ship, and we were fishing for cod, and one of our colleagues got the fishing line completely entangled, and I was I'm not so big into fishing, so I was oh, you give that to me. I'm trying to disentangle. For 10-15 minutes I was trying to disentangle this stupid line, right? And this stupid nylon rope. It was just a big mess. And then the cook from the ship was just hanging out, checking what we're doing when the fish is ready so he can take it to the kitchen. He was looking at my pathetic attempts to disentangle this fishing rope, and he came over and he was so, our communication was also tricky because they speak Danish and a little bit of English. I speak no Danish at all. And he was basically, "Girl, what you doing here?" It's I was I'm trying to disentangle. And he was you pull here, and here, and then, and it's just, I was what did you do? And he was yeah, don't you see where you have to pull? It's no. I was explain. And he was I can't explain. You see that? Don't you see where you have to pull? Because they grew up with entangled fishing rods all the time, and they see exactly where they have to pull so it disentangles, right? And they are out there in nature fish hunting and whatever, and they just know how things are, and they couldn't explain to you why that is, because it is just how it is, yeah. Right? Which a Western scientist can't accept, because we don't know how it is, because we need whatever natural law explanations for that. And this is, I think, what makes communication so hard to really, and it's a two-way communication issue, of course, but I feel like the scientists have to put the work in to really be open for the communication and to really appreciate that someone is like, this is how it is, can't you see it? And don't ask them to explain it to you, but, figure out yourself why that is and go back with like, this is my idea. Can we talk again maybe? I think I'm a bit smarter now.
Yeah, there's a certain intuition and like comfortableness that you get whenever you sit with a problem for long enough. And you're totally right. Like the way in which you ask questions and the way in which you get information dictates the way that you perceive the world. And so there's things that, people sitting in the problem for not even a problem, but they're just like experiencing things day to day, and they just think, oh, this is the way it is. This is probably when it's going to happen. I'm curious about the nonlinearity between all these different parameters, especially when you're modeling. I know that can really increase the difficulty of your modeling. And so maybe let's start first with density and temperature and salinity. So temperature and salinity, it's two independent variables spitting out one dependent variable, which is density. And I'm sure that salinity drives thermal properties of water, which is going to drive the temperature, which drives density. And there's just like so many examples of nonlinearity. Can you talk to me a little bit about that?
Well, so it's a highly nonlinear system. When we model, we make all kinds of assumptions to make it a bit easier. So one of the assumptions that is in basically every bigger ocean model is basically a shallow water assumption. So the ocean is much wider than it is deep. So anything that happens in the vertical is kind of like not playing a big role, which is valid for a lot of things, but especially for like turbulent mixing processes and so on. This is kind of tricky. And then there's a lot of things that are parameterized in ocean models, like, of course, turbulent mixing, but also like the internal wave field is kind of, you don't resolve every internal wave. In most of the ocean models, you basically have ideas of what of a bulk mixing internal waves are doing. And there's a lot of uncertainties. Some arise from we just don't know any better, so we have to guess. And some are like, oh, we just can't resolve it because we don't have the computational power to, resolve every square millimeter of the ocean. We are rather talking about like square kilometers in one grid box. So anything that happens within this grid box, we kind of have to, eyeball. And there's a lot of things happening. And even though we have quite a lot of assumptions in the models, also the models are quite nonlinear. Like there's a lot of things interacting, and it's oftentimes not straightforward to figure things out. However, linearity, yeah. And you can make the equations, you can approximate the equations linear, so you can better backtrack what errors you make, where things are coming from. And despite it being oversimplified, this is also like a really, really powerful tool. So what we use here at UT with our big thing is we have adjoint models that not only calculate the ocean state forward, but they also can calculate backwards why something happened here. So, and this is good for like two things. One is better models in a sense of you measure temperature here and you see there's a misfit with your model temperature, right? So model says it's 1 degree, data says it's 2 degree. And then you ask yourself, but why? Where does this mistake come from? So you basically take this temperature bias and you calculate backwards. Where was this temperature advected from? Was it a boundary conditions that we fed too warm water in or too cold water in already? Or was it like there was not enough atmospheric cooling? Or was the mixing not strong enough to like get the temperature out or whatever? So you can trace back where your bias comes from, and then you can adjust exactly that. So like when you have like boundary conditions for the model or initial conditions, you can adjust those because they are guesswork anyway. If you have like the atmosphere-ocean transfer not right, you can adjust the coefficient there to make it better. So this can help you to improve your models in a way that makes sense. You're not forcing your model to make the right value at the point where you have the measurements, which violates physics, right? You can't just say, oh, you're 2 degrees here, when your model actually said it's 1 degree. Like, you can't force it. This you can, but it violates physics, right? But you can adjust the model equations to make a better job, to reduce that misfit. So that's a very powerful way of using data to make a better model that is internally consistent, right? That doesn't lose energy somewhere, or it's just like, that's a good, cool standalone model. But the equations have been optimized to give the best fit to observed data. And this is one thing we do at UT here. And another thing where you can use this backward tracking for is also when you want to know why a certain thing happens here. So if you're interested in like the water temperature near coast, because that's important for your fish, right? You want to know what's the temperature here and why does it change. You can trace back, does that come from local atmospheric conditions, sunshine, no sunshine, or does that come from 3 weeks ago, sunshine conditions in the North Atlantic, or does it actually come from the strength of some transport current that advects water over the course of 6 months before that was here, and it's the local conditions there. So you can basically connect processes across large scales and large time scales, and say the effects we're seeing here, the properties that are set here in this area I'm interested in, what are they influenced by? Is it local processes, or is it teleconnections to somewhere? And that's a very powerful tool because it also can relate your local conditions to bigger scale El Nino, La Nina, whatever oscillation patterns, where you can say hey, in years where you have La Nina, prepare yourself for lower water temperatures, which whatever effect it has. But this is a very powerful tool to also predict what's going to happen on a very small local scale using our informed ideas about the bigger ocean.
Yeah, that's amazing. It seems really good for troubleshooting. So if something weird is happening, you can just trace it back to what the source of that is. I know in a lot of these models, and at least in some of the kind of definitely not as sophisticated, but the modeling that I've delved into, it can be really hard to find where things happen. And that can be a big challenge to okay, I'm getting this really weird output right here. It's I'm trying to make it return to some kind of steady state, but it's running away from me. I don't know what the exact mechanisms are, so I have to continuously iterate through and painstakingly find out why. So yeah, that seems really awesome.
And in some, this is what we typically do when we analyze model results, right? It's we see this cool feature, but why? And this is a great systematic way of figuring out the why in a, without the iteration sense. So yeah, very, very good tool.
Can we go back a little bit to those benthic environments in the coral? Could you tell me a little bit more about that?
Oh, I'm not sure if I can, because this is my project partners in Greenland that do corals. We have some hypothesis about why corals are where they are, but I'm absolutely not an expert on their physiology and their preferences. And is there anything specific you want to know?
I can't think of anything super specific. Yeah. With Greenland, it seems from what you've been saying so far, and I'm trying to find similarities and differences between the problem in Greenland and then the problem in the Arctic. And it seems in the Arctic you have these continental shelves that you have river water coming off, and then these sediments at shallower depths are getting transported up and are kind of maybe talking to isn't the greatest way to say it, but you have sediment transport from shallow shallow regimes or shallow areas into the deep water. But it seems like with Greenland, you have stuff coming from the deep that's kind of working its way into the fjords over the sill and stuff. Is that a accurate way to?
Yeah, it actually makes a lot of sense, right? I mean, we are all interested in the connections between, shallow and deep, coast and ocean, and it's all about transport and exchange processes. But yeah, so in the Arctic, we're often concerned with what happens at the shelves and how it gets transported into the interior, because we don't really think about the feedback of like the interior to the shelves, because the shelves it's way more variable, it's way more interesting, and the deep Arctic is kind of like, always the same. But yeah, in Greenland shelves, Greenland fjords, there's a lot of impact coming from the deep ocean into the fjords, and also then from what is the upward transport of this deep ocean to the surface and how that affects the ecosystem. So yeah, it's a great way to look at it. And also for corals, one of the things about the distribution of corals is, so they have like some preferences of they want to have some stronger current velocities, not so much sedimentation, relatively fresh food. However, one of the things that we found determines the distribution of corals in the North Atlantic, not Greenland, but in the North Atlantic, is actually connected to a certain ocean current that forms like a highway for coral larvae from coral colonies in Norway that flows south, and everywhere along this current, like this highway, you find coral mounds. And we think this is just a very practical result of like, you need a way to transport the coral larvae so you can start a coral mound, right? Because if you can have all the nicest conditions for corals, if you don't have a single larvae, this is not going to grow, right? So these ocean currents are really connecting different coral habitats, and the transport of larvae is one of the critical things. If you don't have a supply of baby corals, you can't grow adult corals, right? So this seems to be one thing that is really important. And I'd be curious to also see if that's the case in Greenlandic fjords, because the current velocities are relatively slow, but then the fjords branch out, right? And then there's like deep parts of fjords that are like sealed off a little bit, where I would imagine the deep water exchange just happens so slowly that it's not enough to transport anything in there, while branches of the fjord that are more connected because there's no like obstacles between them and the current velocities are maybe a bit higher, if they have, if the ecosystems there are like communicating a bit more connected, if there can be an exchange of larvae, and if that probably is one answer to why is coral where coral is, if the currents that transport the larvae is one of the things.
Yeah, and it seems like the depth is more variable in the fjords than when you look at like this really grand scale, huge Siberian slope. And then with those Siberian slopes, I had it in my mind and it just left me. This usually happens about once every episode, once or twice. With the rotational force that you're talking about, so I guess fast forwarding to like towards the beginning of our discussion, you have these waves that are kind of washing themselves up onto that slope, and then you also have this like perpendicular acting rotational force, right? So does that change the direction of the waves to where they're hitting it kind of diagonally?
It kind of does. So imagine if you had no Earth rotation and you would displace the surface of the water, pile up the water off the coast, and then you would release the wind that keeps it in place. It would just go like back and forth, right, from one side to the other side. But what Earth rotation is basically does, it turns the basin under this wave. So what you see is that this up and down movement actually propagates along the rims of the basin, which is the Arctic Ocean. So instead of like a back and forth slushing, which it still technically is, you see a wave crest that travels along the rim of the Arctic, right? This is what rotation does, right? It makes the back and forth sloshing motion to what appears to be a wave. I mean, it is a wave, right? But it was also a wave when it was just like, left, right, and rotation just makes it a propagating wave.
That's okay. That really helps me understand. That's really cool. So there's like almost this one huge low frequency wave that's kind of traveling around.
And around the Arctic, right?
Yeah.
We're talking about kind of like a bucket of water, but it's huge, right? This is like thousands of kilometers in diameter. So, and this is something I really find interesting, that, the forces that move water and the water movement alone is powerful enough to have like a wave crest travel around the Arctic, well, at least once, and let so distant regions communicate with each other, like connecting over so long spatial scales. That's so much energy in that water.
Yeah, it's amazing. And there's like water coming up from the Atlantic and then leaving the Atlantic and then coming up from the Pacific and leaving the Pacific. And you basically like take all of this water from these warmer oceans and then circulate it into this like big kind of really cold, weird melting pot. And then you have all of this ice on the top. So it's not a traditional ocean in the sense that like there's a lot of heating at the surface because a lot of that radiation is being reflected, and ice is also a really good insulator. What about the surface processes are more unique in the Arctic? I know you're mentioning like the fresh water and things like that, but like do we see more mixing at the surface in, say, the Atlantic when there's not ice over the top?
Yeah, so I mean, the surface processes are completely different because in both oceans, like in an ice-free ocean, also in an ice-covered ocean, you have turbulence at the surface, but the source is super different. So in an open ocean, the turbulence comes from, the wind blows, the wind makes waves, the waves break, it's wind-driven mixing. And in the Arctic, when you have an ice cover, the wind is basically, the only thing it does is pushes the ice. And then under the ice that is pushed over the surface ocean, also drags a bit of the ocean with it at the very surface, you have friction under the ice. So in frictional turbulence versus wave-driven turbulence, this is just two different mechanisms, right? So it has a different flavor. And this is also why it's so hard to model turbulence in the Arctic Ocean, because all the turbulence parameterizations in the model that we have were made for open ocean conditions, for wind-driven, wave-driven turbulence, not for frictional turbulence. So, and we just basically take these equations and put them into the frictional regime, and then we are very, surprised because it doesn't work very well. It's like, oh, no shit, Sherlock, huh? So, and so this is one of the things we really need to work on to better understand how the surface regime, especially the vertical transport, works under ice, because it's just different to the open ocean. You can't just take the equations for the open ocean and plug them in and hope for the best. That's what we do, right? But you shouldn't. There's better ways.
Does it take more energy for the wind to transport ice? Or I guess,
it's harder.
Does the ice have more inertia than just like a non-ice surface?
Oh, that's a good question. I don't know that. What I know is that it's harder to get the energy from the atmosphere into the ocean when there's ice in between. Because moving the ice already takes so much time, and then you only have like the friction, which actually decelerates the ice a little bit, versus in the open ocean where you can transfer the energy to waves, which is just like a resonance thingy, which is much easier. So.
And how thick is ice? Let's say, like in winter, what would the maximum average thickness be?
So when you don't have ridges, so colliding things that form ridges, winter sea ice is up to 2 meters about. So at the end of like an ice flow that started to form in fall is approximately 2 meters at the end of the ice growth season, which is quite a bit. So in American units, it's like 6 feet.
Yeah, that would be
a human.
Yeah, about
a bit more.
Yeah, about
very
my
tall,
height.
basketball player.
Yeah.
Yeah, and then when it starts to melt, that goes relatively rapidly. So when we started to sample, melt season was already in progress, and the ice was like about 1.50 meters, so more a gymnast height than a basketball player's height, like a what's that, like 4.5 feet or so? Is that a relatively small human?
Meter 50 is pretty short, I think.
Yeah. Like a short human, short adult height. And over the course of like 2 months or so, it melted down to like 40 centimeters, which is maybe like 2.
It's
like
a little bit
this.
over a foot. A foot is 30 centimeters, I think.
Yeah. So it went from like 4 feet to 1 foot over the course of 1 foot over the course of 2 months. Yeah, and then it gets very thin, and then at some point it breaks, because. And this is can I one thing about surface waves in the Arctic, which is really, really pretty. So, the open ocean, there's always waves, and it always looks like a little bit messy because there's long waves and then there's short waves, and it's kind of like very irregular surface movement. But ice attenuates wave energy, right? Because the waves have to lift up the ice that is work, so the energy dissipates, and the energy of the small waves, like the high frequency waves, dissipates faster than the energy in the long waves. So what happens when you are like at the ice edge, the ice still moves like a little bit, but then very quickly the high frequency waves go away, and all that's left is like extremely regular, long, low frequency waves. And when you're close, like in the sweet spot where you still have these waves, but not the high frequency waves, and you stand on the bridge and you look down, it looks like the ocean is breathing, because you really have like these huge, long, regular wave crests and troughs, and it looks so incredibly pretty. You just
really
stand
cool.
there and you can see this ice like going up, going down, and like it's so long. It really looks like a huge animal breathing or whatever. It's so fascinating, and you can stand there for hours and just look at that.
Is it like a huge traveling wave that's moving through, or is it like
it's basically just sea swell. So, surface waves that are relatively old and big, and they can penetrate halfway deeply into the ice pack laterally. So, you have like this normal wave climate at the open ocean, and then what goes into the ice gets dissipated really quickly, and it filters out all the high frequency waves and only leaves like this long frequency, very regular waves that go in for a couple of kilometers, I guess. And
that's really cool. Let's see. Oh, I did have another question about the spatial variability of the thickness of the different layers. So thinking about it not so much as like a one-dimensional or two-dimensional profile, but over 3D space. Does that halocline kind of thin in certain areas?
It is relatively stable. It does thin in certain areas or even completely disappear. And that is connected mostly to what water is on top of it. So if you have like a lot of river water mixed into the surface water and it's relatively fresh, you have a very strong and also thick halocline. Whereas if you go to, the fresh water takes a certain route in the Arctic, and if you choose to take the other route, you end up in a regime where you have very, very little to no river water in the surface layer. And then your surface layer is actually pretty saline. And if the salinity of the surface layer is roughly equal to the deep ocean salinity, then you have no halocline anymore because you don't have salinity increase. And then it's gone. And there's places in the Arctic, especially in the eastern Arctic, where that regularly happens. If you just have no fresh water on top, you have no halocline. And that really makes for a very, very different regime. So all the transport processes are different. So you have much deeper mixed layers. You have much more exchange between the deeper ocean and the ice surface, versus when you have like this fresh water on top and you have this sheltering halocline and everything is just stays where it is in the vertical. So there's huge regional differences in the Arctic.
Just for convention's sake, I know this is like something I've always been confused about with the Antarctic. When you say East Arctic, do you mean the Eastern Hemisphere?
When I say East Arctic, I mean the part of the Arctic that is close to Norway and Greenland, close to the Atlantic.
Okay, gotcha.
And the Western Arctic would be the part that is more Pacific water influence, close to Canada and Alaska.
Okay, gotcha.
So we divide the Arctic, which is in the northern hemisphere, into west and east. Which just, the eastern part is more the Atlantic influenced side, the western part is more the Pacific influenced side, and it's just a regional difference.
Okay. And when you talk about this like low frequency wave that's circulating around the perimeter of the Arctic, how is that changing those layers? So you have like the obvious like wind generated kind of internal and subaerial waves that are kind of washing up on that Siberian shore, but then there's also this force that's going around. Yeah. And is that like modulating different thicknesses of stratigraphic layers? Or?
So like these super low mode continental shelf waves that travel around the Arctic perimeter, they only happen occasionally. So they need certain wind conditions to appear, and then they last for like a day or two, maybe 3, not an expert on that, but then they're gone again. And what they do with the layers in the ocean, they basically lift them up and press them down. Yeah. And that also excites internal waves then, right? Because whenever you lift up and push down interfaces, this is kind of like, if you have like in CrossFit when they have these ropes and you like wobble them on one side, the wobble continues. So this is the same with the layers, right? You lift them up, you push them down, and that basically would excite an internal wave that would travel along the interface. However, because these waves that go around the Arctic are so low mode, so low frequency, the internal waves they do are so low frequency that they can't travel away. Because we talked about that earlier, internal waves can only live or freely propagate below certain latitudes, and the Arctic is way too high up to allow for such low mode internal waves. Mm-hmm. So basically the energy can't escape, it's trapped, and it dissipates locally. And this is a big question of where and how much of this energy from like these waves that go around the perimeter actually dissipates. Where does it make the mixing? Does it happen like everywhere all the time? Does it need specific like complicated topography to do that? Mm-hmm. Good question, no answer.
Yeah, it's also, I'm curious whenever that wave, which there might not be an answer for this question, it's just like curiosity of mine, whenever it passes by the Bering Strait and then the strait in between Greenland and Europe, and how
does it jump over?
Yeah, how does it jump over?
This is such a good question. Yeah. I can't wrap my head around that. But it obviously happens. So there was a publication a couple of years ago that describes these waves, and they find connections between a wave like, that was somewhere in Siberia, and then it was in Canada, and then it was on the other side of the Fram Strait again. And I also feel like that they need a boundary. But yeah, this is, I don't know.
Yeah, especially when you think about like, you would be injecting warm water into there, so there would be that like scraping off the carrot, but then you kind of perturb everything and then maybe create some like very localized turbulence because you're generating an internal wave, but it can't propagate, so it just kind of is it a kind of violent dissipation, or is it kind of just more calm? And
so what we observed was very violent. That was like this event that homogenized like 300 meters of water column, right? This absolute explosion underwater. That might be a local effect. Maybe it's super different in other parts of the Arctic. I have no idea. So that's a good question. Further research is needed. Huh?
Yeah. So we're kind of reaching the end here. At the end of every podcast, I like to give you the spotlight and allow you to mention anything that you wanted to mention but maybe didn't get to, or if you want to share any upcoming research or you have anything that you want people to check out, the floor is yours.
Oh my God. I think I would like to acknowledge and thank all the people I could work together with in like my past 10 years of doing science, because there's, especially polar research is such a huge teamwork thing, right? There's like from practical standpoints, equipment is just too heavy to carry it alone, to, people that bear guard you. And then when it comes to science, I'm relying so much on the expertise of other people because, there's so much that you need to understand. And I just halfway understand a tiny fraction of it. So I need other people that also understand other tiny fractions to connect with, to come up with, better scientific results, that I think we always have to keep in mind to thank the people that work with us. And I'm so grateful for all the people I was working with before, and also my working group at UT now is really amazing, and they have like these fancy model things that I told you about. So yeah, I think that's maybe what I wanted to end with. Like, thank you for all my collaborators in the past 10 years that brought me to where I am now.
Yeah, well, thank you so much for coming on, and best of luck with the NSF grant and everything else to come. Yeah.
Great, it was a pleasure.